We've had a look at series circuits and we've had a look at parallel circuits, but now we're going to look at series and parallel as a combination. As you can see here, I've got two circuits drawn. This one's got two resistors in parallel and another resistor sitting over here. And this one's got three resistors in parallel with another resistor sitting over here. When you're trying to solve these type of problems, and keep in mind that these are just two simple ones, is to look in from this end of your circuit and work back towards your supply. And you can see that the first thing we run into here are two resistors in parallel. And over here we've worked that out, so we've got R2 and R3 in parallel with each other. We're using the product over the sum formula, and as you can see there, we've worked out our numbers right for that and come out with a resistance of 2221.8 ohms. So that part of the circuit represents that value there. We've also got this resistor, and when you bring these two together and work out your parallel, now they're in series. So you basically make that one resistor. So that 1.5k is now in series with this 2221.8 ohms. So we've got R1 plus the two parallel resistors. So we've got 1.5k, 2221.8. You end up with 3721.8 ohms for that little circuit. And we've got three resistors in parallel. Notice I've put the resistor here. It was at the top, now it's at the bottom. Makes no difference. And the first thing that we do is look in from this end, working back towards your supply. And we've got three resistors in parallel, so now we use this formula. You can see here that we do that, 1 over R2, 1 over R3, 1 over R4. And then we work all that out, come out with these nice big long numbers. We end up with that. And then we take the inverse of that and we end up with 199.996 ohms, call it 200 ohms. And again, we have to account for this resistor. So it doesn't matter if this resistor is here or up here. It is now in series with these three parallel resistors. RT, or your total resistance, is equal to R1 plus the parallel combination. So here we've got 1.5k plus 200 ohms, gives you 1.7k ohms. Now that we know what our total resistances are for each of the circuits, we can now work out what the current is if we knew what the values of the supply voltage were, and we'll have a look at that in a second. So what we've done here is just worked out what our total current is. I equals V over R, so V is our supply voltage, which is in this case is 9 volts. Our total resistance is what we calculated, 3721.8. We could have made that 3722. Complete this calculation, we end up with 2.42 milliamps of current flowing. In this situation, we use a 12 volt supply, so VS, which is your supply voltage, your total resistance 1.7k, and we end up with 7.06 milliamps of current. And again, that's what's leaving the battery, passing through this resistor, then your individual branch currents coming through, combining, and then coming back to your battery again. So we've moved on, and as you can see here, we've got our total current, so that's the current leaving the battery and coming back to your battery in both cases. So the first thing that we've got to do is work out the voltage drop across R1. The voltage drop there is the total current times the resistance, so V equals I times R. We've got 2.42 milliamps and a resistance of 1.5k ohms. So that voltage drop across that resistor is 3.63 volts. So that's what's dropped across there. So the voltage drop across R2 in parallel with R3 is equal to supply voltage minus the voltage drop across R1. So you've got 9 volts minus 3.63 volts. So the voltage across the parallel circuit should be 5.37 volts or close to it. So what we've done here is built the series parallel combination. What we're going to do now is just check what the overall resistance is, and we'll check what the resistance of the parallel circuit is and see if that matches what our calculations are. Now, it won't be exact because you have tolerances in your resistors, so just because this is marked 1.5k, 3.3k and 6.8k does not mean that is what their values are. These are plus or minus 5%, and they are within tolerance, but they could be above or below those values. So the first thing we're going to do is just look at the overall resistance. So we're just going to go across the output here, and we're getting a reading of 3.7 or close to it. Yep, about 3.699. If you remember from our calculations, we had 3.721 k ohms, so we're getting pretty close there. So let's have a look at the parallel combination. So what we'll do now is just measure across the parallel, and if we do that, we just go from top to bottom, and we should end up with 2.2k. You can see here that we're getting 2.21 or close to it, so that measures out. So you can see from our calculations for the parallel and the combination of the circuit that we're pretty close to what we calculated on the actual board. So I'll just check. We've got a 9-volt supply. Well, it's actually reading 8.993. It does vary around a bit, so it's close enough, right, for us to get some close measurements. So we're just going to look at the voltage drop across R1, and that should have been about 3.6 volts, and you can see here we're getting 3.623 or thereabouts, so that's close to what we calculated. And the voltage drop across the parallel combination should be about 5.37. We're getting 5.366, which is pretty close to what we calculated. So what I've done here is set up right, the larger meter here, the LP370 for amp, to measure the amps. And I'm just going to use this one to measure the voltage that we're putting in. Anyway, that's close to 9 volts. So you can see with a 9-volt supply we're getting 2.45 milliamps, and what we calculated was 2.42 milliamps. Now that's the total current being drawn by the circuit. So what we'll do now is just measure the current through here. Our calculations on the board, we should have got 789.7 microamps. Measure that. Now I've taken the link out and I'm going from here to here, 781 microamps. So you're getting a slight difference there, but again it's just the tolerances of the resistor, and probably the right supply voltage is varying around a little bit, but you can see it's very close to the calculation that we did on the board. So we measured the 6.8 k ohm resistor, and now we're measuring the current through the 3.3 k ohm resistor, and that should have been 1.63 milliamps. Now I've just taken one of the legs off, right, the negative rail, and if I measure the current through that, we're getting 1.6223, which is pretty close to 1.63, which is what we calculated. And again, that slight variation is going to be with reference to tolerances of that resistor, but again it proves that the calculations are in the ballpark, and our measurements are kind of matching our calculations, taking into resistor variations.